Hey, hello everyone. Can you hear me clearly? Let me see. So, yeah, if you can hear me, could you please type something so that I know that there is no problem with my microphone? Eh, something strange. Let me type. So we are about. Oh, thanks very much. Okay, so we are. Thank you very much. Okay, so according to the school's policy, we are going to have a distance learning mode in these 2 weeks, and then I expect that we will continue to have this learning mode until the end of this semester. So most probably, your exam 3 will also be an online exam. And so the purpose of today's discussion here is a quick summary of what we are going to talk about this week. So first of all, there are videos, as I have mentioned to you all, that we can get from my Google Drive. So those are videos from last year's lecture. So we can take a look of them and then use that as the basic materials for learning. And then for today, yeah, what I'm going to do here is I'm going to give a summary of the videos that you are going to see. So let me start. So So last time in the last lecture, we are still in lecture 21, talking about the how to solve two sets problem. Okay, so let me see enter full screen. So let me quickly recap. So this is a two sets problems definition. So we are given a formula f, and then this formula f consists of n variables, and then each of the clause in the formula f has two literal, so they are all together. So what we want to do here is we want to find an algorithm for checking whether there is a certain assignment of the variables to either true or false, so that the overall result of the formula becomes true. So this problem can be solved already efficiently in linear time. But what we are going to do here is we provide a randomized algorithm. This algorithm motivates us to design an algorithm later for solving three sets. Okay, so a quick review of this algorithm is, so we have the formula f, and then we have n variables. So we start with an arbitrary assignment of truth value to these variables. So maybe x is true, y is false, z is false, and so on and so forth. And then we are going to repeat a certain number of times, and then we will check whether the assignment will make the formula f to be true. If it is the case, then we stop. If it is not, then we will repeat doing these two steps. First of all, if an assignment is not going to satisfy the formula, then that means that there must be some clause that is currently not satisfied. In that case, we will pick a random clause from these clauses that are not currently satisfied, and then we choose uniformly at random one of the literal to change the corresponding truth value. Okay, so we modify the assignment using this step, choose a clause not okay, and change one of the variable. So by doing this a certain number of times, then we will check whether we have already obtained a valid assignment, making f to be true. If it is the case, then we will say yes. So the formula is satisfiable, and then we get the assignment. Otherwise, we conclude that f is not satisfiable. And somehow, this process can be captured by a certain chain, but it is not a Markov chain. Okay, so I'm using the wordings here. So this is an example that we've seen last time. So suppose that the formula is this one, and then we see that this formula is satisfiable. For instance, by setting x1 to be true, x2 to be true, and then x3 to be false, then in that case, this part will be true because due to x1. This part will also be true due to x2, and this part will be true due to x3. Okay? And then our algorithm will first do random assignment and do it until we find a valid assignment. So suppose that at a certain step, we find that the current assignment is x1 is false, x2 is true, x3 is false. So false, true, false. What will happen? If it is false, true, false, then this will be false. False, true, false. This is going to be true because due to x2. False, true, false. This will be also true due to x3. So in that case, this is the clause that is currently not okay. So we will see that in that case, our algorithm will pick x1 or x2 uniformly at random and change the assignment. So with probability 50 percent, okay, 0.5, we change f to be t, or we change t to be f here. Okay, we will see that currently we have two variables that are matching between the current assignment and the optimal correct assignment. So x2 is correctly assigned, x3 is correctly assigned, and this is not. But then we will see that by doing random assignment here, at least we will have half of a chance to make our current assignment more closely, a little bit closer to the optimal assignment. And of course, with 0.5 chance, we may be farther away. And somehow we can describe our process similar to a Markov chain like this. But for our case, it is not exactly 0.5 here and not exactly 0.5 here. For our case, we should have more than or equal to 0.5 changing from, so these values here, 0, 1, 2, 3, let me recall, they represent the currency, how many variables are assigned in the same way as in the optimal assignment. So in such a case, then we will see that if we are only having only one variable assigning correctly, then with more than or equal to 0.5 chance, we will go to 2. It is because the current clause is not okay in our assignment, but it is okay in the optimal assignment. So in such a case, that means that a certain variable, at least one or two variables are assigned incorrectly. So in that case, we will have at least 0.5 chance to find a variable that makes us to be better or closer to the optimal assignment. But then the behavior of our case is not truly a Markov chain, because for Markov chain, we cannot have something like sometimes this is 0.5, sometimes this is another number. So what we are analyzing, our problem here is that we compare our scenario with this simplified chain, and this is a Markov chain that we have. Okay, so this time this is a fixed 0.5, although in our case sometimes we may have all the probabilities going from 1 to 2. Okay, by analyzing this chain, what we will see that is the chance of us, original one, reaching the state n, that is reaching the case that we have all the correct assignment, will be less than the chance for this chain to reach, will be greater than the chance for our chain to reach n. The reason is that for our case, we have every time that we go forward, we have more probability, and every time we go backward, we have less probability. And also, in terms of expected number of steps, then if we are at state 2, let's say, for our case, the number of steps expected for us to go from state 2 to n must be smaller than or equal to the number of steps expected to go from state 2 to n in this chain. So in that sense, we can compare our algorithm with the chain here for some property. So if we focus on the Markov chain in the previous page, we can define h of j to be the expected time to reach n starting at j, state j. So h of j, the h here means the hitting time, the time for us to hit what we want. So hitting time if we start from state j. So obviously, if we are already at state n, h of n is equal to 0. We don't need any more steps. We are already at state n. And for h of 0, then we know that no matter what happens, it must be equal to 1 plus h of 1. It is because if we are at this state, no matter what happens, the next step we must go to state 1. So we must spend one time unit or one step to go to state 1, and whatever happens there, we will reach n afterwards. So this is actually by linearity of expectation. But in general, for the intermediate h of j, then it is half of hj minus 1 plus 1 plus half of hj plus 1 plus 1. Half of a chance we go back, half of a chance we go forward. And this is the expected time or expected number of steps that we move from j1 and j minus 1 to n. And this is the case that we move from j plus 1 to n. So the plus 1 here accounts for the step that we need to move from the current state to j minus 1 or from the current state to j plus 1. And solving this, we find that hj is always less than or equal to n squared. So what does that mean? So no matter which state that we are in here initially, the expected number of steps that we need to go to this final state n that we want is less than or equal to n squared. So based on this, this is what we have. Expected time for our Markov chain to reach state n is less than or equal to n squared. And then we have also compared the expected time for the original algorithm to reach state n and for the Markov chain to reach state n. So the original algorithm takes fewer number of steps. So we have this property. So in conclusion, we have this lemma. So assume that f has a satisfying assignment. Then if the algorithm is allowed to run until it finds a satisfying assignment, then the expected number of iterations is n squared. Okay? So in that case, this explains why we have a parameter 2 times c times n squared in the design of our algorithm. It is to reduce the error probability. So we see that the expected number of steps is n squared. So with 2n squared to be allowed, then the chance of going to the final state will be more than or equal to 1/2. This is by Markov inequality. The chance that we cannot go to is less than or equal to 1/2. So it is going to be more than 1/2 if we are allowed 2n squared. So if we have 2cn squared, the chance that we do not find any correct assignment, so you can think of this as we have c batches of 2n squared steps. So each of them you have less than 1/2 not finding the optimal assignment. So in total, when we have c batches, then the probability that we cannot find will be less than or equal to 1 over 2 to the power c. So that's why we will have probability 1 minus 1 over 2 to the power c to be able to find the correct assignment. So this explains the whole algorithm. So let's record the algorithm looks like this again. So here, this step is we will run it. Think of this as c batches of 2n squared runs. Okay, so for each 2n squared, then we have half of a chance of getting the optimal assignment. So with c batches, we will have more than 1 minus 1 over 2 to the power c chance to get an optimal assignment. So if we do not find it, then either if we find it, that's okay, right? If we do not find it, there could be two cases. Either there is no way for this formula to be satisfiable. Good. Then in that case, we will answer this correctly. No way. But on the other hand, there will be a very small chance, 1 over 2 to the power c chance that it is indeed satisfiable, but we do not find it. Okay, so this is the two-set algorithm. Okay, so let me double check. So yeah, I think everyone is okay with this, right? So yeah, if we are all okay, so let's now move on to the three-set case. Okay, you will see that the algorithm is extremely similar. So this is going to be lecture note 22. So okay, so the three-set algorithm, the difference here is the input. The input formula, this time each clause will have exactly 3 literals. And then we want to design an algorithm to decide if the formula is satisfiable or not. Okay, and let's see. Okay, let's see how this algorithm do. Okay, so let's recall. So what we are going to do here is we are actually using the same algorithm if you look at it. So we will start with an arbitrary assignment, and then we will repeat many times. Okay, so we will decide this m later, and then every time if we still find some clauses that is not satisfied, then we pick one, and then there are three literals inside. We will choose uniformly one of them and change the assignment of that variable. And again, after m steps, if an optimal assignment, a valid assignment is obtained, then we will just return it. Otherwise, we will conclude that the formula is not satisfiable. Okay. So we can actually follow the same approach as before to analyze what will happen. So you will see the definition here, same as before. A star represents a certain optimal assignment. AT represents the assignment for our algorithm at the tth iteration. And then here, somehow, we will associate this with the Markov chain like this. So here we will see that if we have a certain assignment that is, let's say, matching one variable, the assignment of a certain variable in our algorithm's assignment is equal to that of the optimal one, then you will see that there is at least 1/3 of a chance to move to state 2. Yeah, because there are three literals. So we are sure that in the optimal assignment or in the correct assignment, these three literals are not going to be exactly the same way as we assign it with the way that optimal is assigning. By picking a random variable to change its value, then we'll have 1/3 of a chance to pick this correct variable. So there is at least 1/3 of a chance to move forward and at most 2/3 of a chance to move backward. And in such a case, then we will, again, as the argument as before, our scenario or our algorithm is not representing a Markov chain. It is because the forward probability could be 1/3, 2/3, or 3/3, depending on what the current state is, current assignment is. So what we are going to do here is we are going to associate the scenario with a simplified Markov chain as follows. So we will have a fixed 1/3 chance for moving forward and a fixed 2/3 chance of moving backward in general. And then here, this is the exception. If we are at state 0, then we must be moving to state 1 with all the probabilities. And similarly, if we are already at state n, then we are going to stay there forever. So with probability 1, we're still at n. But in general, it is 2/3 going back and 1/3 going forward. Okay, so if we proceed as before, then we are going to solve a formula like this. So we define the heating time if we start at state j as before, and then we have hn is equal to 0, h0 is equal to h1 plus 1. And here, this is the change. H of j, it is equal to what? There is 2/3 of a chance of going backward. So 2/3 of a chance, you will need one step to go backward, and then an extra hj minus one step to go to the final state. And then with 1/3 of a chance, we are going to move forward. So in such a case, we spend one step to move forward, and then an extra hj plus one step to move to the state n. Now, if we solve this formula, so this is the set of equations that we are going to solve, then somehow we can solve it exactly by finding that h of j is equal to 2 to the power n plus 2 minus blah blah blah. And then actually, h of j, what we can obtain is like this. So it is exponential in n. It is really like 2 to the power n. So on average, what does that mean? It takes 2 to the power n step to find a satisfying assignment. But with 2 to the power n steps, we can do something else. We can really try out all the possible assignment of these n variables, because all the variables are Boolean variables. They are either true or false. So there are only 2 to the power n different assignments in the whole world. So in such a case, if we are using 2 to the power n steps in our algorithm, why not we just start with checking each of the assignments one by one by brute force. So in that case, this algorithm, this method that we have here, this method here is not good. Even if we are going to find this in the expected time, then this expected time is already running in 2 to the power n steps. No good. So we need to do something a little bit clever. So okay. So first of all, we this is the key observation. Okay. First of all, if the algorithm starts, then as it runs through more steps and more steps, it is more likely to go backward than to go forward. So here, the longer that we run the process, the more likely that we will move back to 0 than to moving to n. So in such a case, it is not good. So what we want to do here is we want to restart the process after only a small number of steps. So what does that mean? Okay, so here, remember that at the beginning we are choosing a random assignment, an arbitrary assignment. Okay, and then we start moving in this chain. Now, if the arbitrary assignment that we are choosing is close to this end, then it is good. Then maybe after certain small number of steps we can reach n easily. But if we are starting at some early stage like this, then maybe even if we do many steps, we cannot go to n, because the more steps that we have, the more likely that we go back to 0. So in that case, what we are going to do here is that we will restart the whole algorithm after a small number of steps. So we are actually trying our luck. So by trying our luck of doing the arbitrary assignment, we hope that we can get an arbitrary assignment that is close to this region, so that after running some steps, we can reach n. And then, so we are not going to keep on checking for a certain case for a long time, and then because the longer that we try, the more likely that we are not okay. So we will restart and then try our luck. So this is the new idea. So we are going to put the repetition in the outer loop. So we are going to repeat m times, but then what we are going to do here is that for each time that we are going to restart, we will choose an assignment, a random assignment again. So this is the purpose of restarting. And after restart, we do not run it for a long time. We run it for only 3n times and try our luck. If we are lucky, good. Then we find the assignment. If we are not lucky, then we will repeat this, restarting, and so on and so forth. Now, why do we have this one and then we will have an improvement? It is because there could be a lot of good assignment that we can take at the beginning, so that after running 3n steps, we will really reach the final state. So here, let's do the analysis of this modified algorithm, and then we will determine the value of m later. Okay, so here we let Q to be the probability that the process will reach A star in 3n steps when we are starting at a random assignment. So we are analyzing the probability of running once this AB part. Okay. So Q is the probability that we will be successful in one loop here. Okay. So in this loop, we check a random assignment and then run 3n times. This is one whole big loop. Okay. And then we let Q, and then we have a subscript minus J, to be the probability that if we start from only j steps away from the final, what is the chance that we can reach the final step in 3n extra steps? Okay. So we are going to first analyze this. So eventually we want to get the Q. The Q will determine the number of times m that we should run for the whole algorithm. Okay. If Q is large, then we will run m to be small. If Q is small, then we run m to be large. Is that okay? So we have a following observation. So we will establish a relationship between Q and then Q minus J's. Okay. So the key observation here is that if we start at only a location with j variables away from the optimal, the correct assignment, then we will see that as long as we don't go back many steps, let's say less than or equal to n steps in the algorithm, then we will be reaching the final state, right? Because for instance, if we go back k steps, that means that we will have j plus, so we have altogether 3n steps, right? So we will have at least j plus 2k steps to be moving forward when k is less than or equal to n. Then in that case, we will reach the final final state. So in that case, we will see that in order to have q minus j, one way is we have this particular case, the probability of E1. E1 means that E1 means the event that we are moving at most one step backward. E2, one step, two step backwards during the whole running time. EJ means that J step backward. Okay, yeah, because we are at Q minus J. Okay, but then what we are really bounding this probability is just a very crude approximation. We will see that the union of these all events must be a superset of this EJ. So in that case, the probability of the top line here is greater than or equal to the probability of the bottom one. And for this one, we can calculate exactly. So this EJ here means what? EJ here means that out of 3J steps, exactly J steps are moving forward, moving backward, and exactly 2J steps we are moving forward. So this is the probability that we can compute, and so on and so forth. So we have an approximation of this Q minus J value to be something like this. Okay, so you can check the algebra, the simplification at home. The high level here is that we have a relationship of Q minus J with this value here. And so the probability of Q that we want to compute here is that, first of all, we want to find out how many chance that we are starting with the arbitrary assignment that is J steps away from the optimal. So with this probability happening, then there is at least Q minus J chance for it to go to the final state. So this is actually a weighted sum of what is happening. So this is by the definition of probability, right? And the after that, then this is just algebra. So we can plug in the formula for Q minus J here. So this is Q minus J here. And then the probability of Xj here simply is Cn choose J, because we are starting with the random assignment. So there are n choose J chance for n choose J. Okay, sorry, n choose J times 1 over 2 to the power n chance for us to be selecting exactly J variables that is not the same as A star. Okay, and after simplification, we will find that this probability Q is something like this. So forget about this part. It's something like 1 divided by 1.33333 to the power n. And if you are now familiar with if this is the probability that we will be successful. So what should we choose M here? So to make this a case where we are successful with high probability. So it's not difficult. So what we are going to do here is, if the chance of this is 1 over 1.33333 to the power n, then what we need to do here is we need to run it for 1.33333 to the power n multiplied with log of n. So in that case, yeah, this is what we do. So m should be set to 1.333 to the power n multiplied with the log of n that I have mentioned here is can be replaced by 2 times r here. So in general, if I set it to be log of n, then you will see that the algorithm will be successful with high probability, because this will now become 1 minus 1 over n. Is that okay? So this is what we can do. Okay, so I think, yeah, that's all. So if you understand the algorithm for solving two sets, then you will find that we can easily get an algorithm for solving three sets. But then this is not enough. It is because the difference between two set and three set is going to be bad if we keep on running with a particular random assignment at the beginning. So we will need to restart it from time to time, and the restarts really help us to solve the problem. Okay, so yeah, I think, yeah, that's all for today. So although it is a bit short, so this is the purpose of a lecture summary. So if you want to have more details, yeah, please check the videos from the last year. Okay, and yeah, if you have any questions, so please send us email. Okay, or we should provide a certain link for you to send us questions later. Yeah, thank you very much. And then, yeah, let's meet again next week. So next week we will continue our discussion of Markov chains, and we will see some interesting problem. This time we will talk about gambler's ruin. Okay, so thanks all, and then see you next time. See you. Okay, bye bye.